Hello, thank you all for tuning in, and today we're going to be discussing and studying math with me. Today we're going to be discussing some applications of logarithms and exponentials, and this material comes from chapter 4.4 and 4.6. The first application that we're going to discuss is having to do with pH values. This stuff is found on page 428 in your textbook. In chemistry, the pH of the solution is defined to be the negative, and that is the logarithm base 10 of the hydronium ion concentration in moles per liter, and a mole is Avogadro's number of molecules. The pH value tells you whether it is acidic, if you get a number way down here, or basic or alkaline, if it is way up here. And it says it's customary to round pH values to the nearest tenth. So that's what we're going to try to do. So this is the equation that we're going to be exploiting as we go forward in this problem. So then the exercise 2, or example 2, says they want you to find the pH of a solution that has a concentration of hydronium ions. So we will use our equation, and the minus is important because chemists like to have these things positive, and so we will put the hydronium ion there, and this then is equal to the negative logarithm base 10 of 6.8 times 10 to the minus 8. And since things are normally written in scientific notation, that's why it's important to be doing log base 10. So this then is going to be equal to minus the logarithm base 10 of, and now we have a product. This is 6.8 times 10 to the minus 8. So this is minus, and then it is log 6.8 plus the log of 10 to the minus 8, because the logarithm of the product is the sum of the logs. So that is going to be equal to minus, you'll plug this into a calculator, and you get, let's see, it would be 0, it's going to be, let's see, this way, it is 0.8325, and there's more numbers there, minus, and then the logarithm base 10 of 10 to the 8 is just going to be minus 8. Now you got some minus times a minus action happening here, but this is going to be approximately 7.2. Now the other way that you can do a problem like this, where you have an equation, is in this first example they gave us the concentration of the hydronium ion. Now what they could do is they could give you the pH value and ask you to find the concentration of hydronium ion. So here the pH value is 4.3. So using the same fundamental equation, what we would say is that 4.3 is equal to minus the logarithm base 10 of the concentration of the hydronium ion. And you could just think about that as being x. So that means I could move my minus sign to the other side, and I could have log, and then I have the logarithm base 10 of this is equal to minus 4.3, so that tells me that this is equal to 10 to the minus 4.3 exactly, and that's approximately equal to, let's see, that would be 5.0, there could be more digits there, times 10 to the negative 5. So that is this example dealing with pH values. Our next example has to do with decibels, and again decibels, the deci stands for 10, and bells is named after Alexander Graham Bell, and so the loudness of sound is measured in a unit called decibels. We first assign an intensity I0 to a very faint threshold sound. Sometimes they call this the threshold of hearing. A person with good ears can hear that sound. If a particular sound has an intensity of I, then the decibel rating D of the louder sound is given by D is equal to, you multiply by 10, to make the number not have a bunch of decimals in it, and then you take the quotient of the logarithm base 10, and this is the intensity of the sound you're measuring, and you take it relative to the threshold sound. So that's what's going on with that, and we'll do an example of this now. And here's the example. Oh, by the way, this stuff is found on page 429 of your text. So now what we're going to do is we want to find the decibel rating of a sound with intensity. Let's see, what is that? Let's see, put some zeros in. That is 10 million times the threshold. So our formula is this: D is equal to 10. This is a logarithm again, base 10, and that is I over I0. That's from the previous page. And so then that's going to be equal to 10. And this is going to be log, and we're going to put, and by the way, this number right here, if you change that to scientific notation, that is 1 times 10 to the 7th. So this is going to be 10 to the 7th times I0 divided by I0. The I0s will cancel with one with another. So I have 10. The logarithm base 10 of 10 to the 7th is 7. And so the answer is going to be, this is 70 dB. And the notation for dB is not really shown in your book, but it is this. And in fact, that's a big deal in the telecommunication industry. So that takes care of yet another example. Now, the next example is significant in that instead of using logarithms base 10, you see that we're using a natural logarithm. So this is measuring the age of rocks. And so the story is geologists, and it's on page 430 in your textbook, geologists sometimes measure the age of rocks by using atomic clocks. And they measure potassium. Potassium always is a K, that's the chemical signal, and argon, and A is the symbol for that. You can find the age of a specimen by this equation. 1.26 times 10 to the 9th, and it's the quotient of these logarithms, and that's 1 plus 8.33 times the ratio of A to K. So what we're going to do is we're going to use this equation to answer some questions. So this first thing says, how old is a rock if the concentration of, if the amounts of both potassium and argon 40 are the same? So what we're going to come up with is that T is equal to, I'm just using the equation that we just spoke of, times 10 to the 9. And then is the quotient, but now you want to be careful because this is the logarithm, the natural logarithm. And recall that what we have is, this is the natural logarithm of, this is 1 plus 8.33 times that ratio. Now in part A of this problem, we're saying that A equal K. So that means that I'm going to add 1 plus 833 times 1, or I will have 9.33. And then I'm going to divide this all by the natural logarithm of 2. So you'll go through and punch this into your calculator, punch this into your calculator, multiply it all together, and what you will end up with is this being approximately equal to 4.06 times 10 to the 9. That means that this rock is 4.06 billion years old. The second example of this says, what if the ratio of A to K, which again is the huge thing that this formula depends on, is how old is a rock, if that's true. So again, we're plugging into the same formula. So we'll have 1.26 times 10 to the 9, and this will be times, now this is going to be the ln of 1 plus 8.33, but now we're multiplying 8.33 times 0.325 because that is the ratio, and when we're dividing that by the ln of 2, And if we do that, and you should practice this just so you know that you can plug in the numbers. First you will multiply those two, add 1, take the ln, and so on and so forth. You will get 2.38 times 10 to the 9. And so these would be the answers to this example. And this example was important because it involved the natural logarithm, not the logarithm base 10. Okay, so we'll move on to yet another example. And this next example has to do with a whole different logarithm. This is logarithm base 2. Now, this is measuring diversity of species. I'll talk about it and then explain why they're using logarithm base 2. One measure of the diversity of species is given by this formula, h is equal to, and you have a whole bunch of p's being multiplied together, where these p's are the proportions of a sample belonging to each of the n species found in the sample. There was a biology project that a student at the College of DuPage did where they went out to some of our lakes and they actually did exactly this diversity study using such an equation. Now, these are proportions, so these are P1 and P2 and so on and so forth are numbers less than 1 because it's really telling you what fraction of the sample belongs to each of the species, and that's why you're going to need a negative there, because when you take the logarithm of a number that is less than 1, you're going to get a negative in every case. Now, the reason they're using logarithm base 2 in this case is that either you belong to a species or you don't belong to a species. Now, that is typical of when you're going to want to see logarithm base 2, because in telecommunications it is a 0 or a 1. In computer science it is 0 or 1. Here you either belong to that species or you don't. So anyway, this is the equation that we're going to use, and it's significant because now we're using a totally different logarithm, logarithm base 2. And this example like this is on page 433 in your text book. Now, this does require us, though, since your calculators don't have logarithm base 2, you want to remember this formula for change of base, and this is on page 432 in your textbook. And so what we have is the logarithm base a of x is equal to the logarithm base b of x divided by the logarithm base b of a. Now, in our case, we want logarithm base 2 of numbers, and so that's going to be and I'm going to choose to use natural logarithm. You definitely want to use something that's on your calculator. So this is logarithm base e of x divided by logarithm base e of 2. And so this is the calculation that we're going to use to change all those numbers into logarithm base 2. And here's the example that we're going to study. The example is, what is the diversity of a community with 2 species? 60 of one species and 140 of the other species. And so we will go and use the formula that we just learned. So h then is equal to the negative of, and here there were 60 of this species and there were a total of 200. So we have that. This is logarithm base 2 of, and it's going to be that same number again. That is 60 over 200. And 60 over 200 is going to be 0.3 in just a moment, plus the other one is 140 out of 200. And this is logarithm base 2 of, and this is going to be 140 over 200. And then we need to close that parentheses. It's way back here. So it's going to be a negative. This is 0.3 times, now this is a logarithm of 0.3, so to calculate this using your calculator, you will do that. And then we will say plus, and this is going to be 0.7, and that is the logarithm base 2 of 0.7, so we will do it this way. And now it is pounding this number into your calculator, and you'll get approximately 0.881. Now, students should really practice pounding this into your calculator to make sure that you're good at using a calculator, because it's kind of the point of many of these problems. Okay, Now, the next suite of problems that we're going to be studying, and this discussion is found on page 451 of your textbook, deals with exponential growth or decay functions. I've talked a little bit about this, and so anyway, here we go. Let y0 be the amount or number present at time z. Then under certain conditions, and these are very general conditions, the amount present at any time t is modeled by y equal y sub 0 times e to the kt, where k is a constant. Now note that y is a function of t, so y is a function of t, and is y0 a constant times e to the kt. So the variable is t, k has to do with the physics of the problem. And notice that when we put t equals 0 into y, we're going to get y0 times e, and that's going to be e to the 0. But e to the 0 is 1, so we just get y0. That's kind of an important consideration as we go through. Let's do an example of this exponential growth. And actually, this is going to be a finance example. And so what we want to do is remind ourselves of the finance problem, but let's talk about it. How long will it take for the money in an account bearing interest at 4.5% compounded continuously to double? And the thing that's important for us to realize is the fundamental formula, which is on page 404 in your textbook, for continuous compounding. It tells us there that if P dollars are deposited at an annual rate, are deposited at an annual interest rate of R, but you're compounding that annual rate continuously for T years, the amount is A equal P times E to the RT. So that is the equation we're going to be using to address this problem. So let's go back to the problem then. We want it to double. So this is our equation. The amount is equal to P times E to the RT. And we want it to double. So we want the amount to be twice what we started out with. So that is going to be 2P is equal to P E to the RT. Now this P is being multiplied by e to the RT, so I'm going to divide both sides by P, and I'm going to get 2 is equal to e to the RT. Now, and we know that R is this, so we now really have this. 2 equals e, the rate is 0.0425, and then this is times t. So this is the equation that we have to solve. And the easy way to solve this is, since the variable is in the exponent, we're going to take the natural logarithms of both sides. So we will end up with the natural logarithm of 2 is equal to the natural logarithm of this, which is just this. So now what we're going to do is we're solving for t. So t is equal to the natural logarithm of 2 divided by 0.0425. And if you do that, what's going to happen is that you're going to get approximately equal to, and you should punch this into a calculator to make sure that you can do it, but we're going to get 16.3 years. Now, one of the things that people in finance do is they talk about a rule of 72, which says, oh, in general, the doubling time is going to be the product of the rate as a whole number times the time in years is approximately equal to 8. And you see here, if we take the rate being 4 and change times 16 and change, you do get close to 72. So that's sort of a rule of thumb that often is used by financial planning types. That was an example of exponential growth. We're also going to look now at an example of carbon dating, and I talked about this with the Shroud of Turin a little bit earlier, but now we actually have a numerical example. Carbon-14 is the radioactive form of carbon that's found in all plants and animals. After they die, this disintegrates and you can determine the age of remains by comparing the amount of radiocarbon in the amount present in living plants and animals with the amount that is found in the fossil or whatever you find. And it's called carbon dating. Now, the reason this works so well is that the half-life of carbon-14 is approximately 5,700 years, so it works very well for that. And so this ends up being the equation that you use, where Y0 is the amount that you find in living organisms, and then Y, T time after the animal perishes, it is going to be decayed by e to the minus, and there's that factor times t. And so that's the physics of the problem that is described near page 453 in your textbook. Now, what we're going to do is work a problem with this, and here is the example we're going to study. This is similar to the example in your book, but like all these examples, it's not exactly the answer, or it's not exactly the problem in your book. So suppose that 800 grams of a substance are present initially, but 2.5 years later, only 400 grams remain. How much of the radioactive substance will be present after 4 years? Well, the equation is this one, and this is e to the minus kt, and for carbon-14, that means that this is, and the problem at hand is 800, and this is e to the and we're going to be using that number that they gave us, and so that would be let's see. This is just a general radioactive substance. This is not just carbon-14, and so we really have to we have a different variable we need to solve for. We need to find out what K is for this radioactive substance. This is not necessarily carbon-14. So what we do know is that there were 800 grams available initially, and we also know that when T is 2.5, it's 400. So we know that this is 400, that is 800, and this is e to the minus k, and this is times 2.5. And now we will divide both sides by 800, and so we will have ln, let's see, not ln yet, we'll have 1/2 is equal to e to the minus k times 2.5. And now what we're going to do is we're going to take the natural logarithms of both sides. So this is going to be the natural logarithm of 1/2 is going to be equal to minus k. We're taking natural logarithms, so these are inverse functions of each other. So we can do that. So we end up being able to solve for k. And we'll find out that k is approximately equal to minus 0.277. So that means that our equation then is y is equal to 800, and this is going to be e to the, and actually I should have said k is approximately, that's positive because there's the minus sign there. So this is minus 0.277, okay, and then we want to find this after 4 years, so we'll put 4 in there. So this is just a calculator problem. You plug in these numbers into your calculator. This is the whole of the exponent, and you're going to find that there is approximately 264 grams present after 4 years. So we had to solve for k first, and then we used that in the balance of the problem. So that is an example of radioactive decay, and we talked a little bit about carbon-14. These numbers were a little tamer than the carbon-14 example. The last example that we're going to discuss in this video lecture is called Newton's Law of Cooling, and I did really talk a little bit about this before in the lecture, the video lecture over chapter 4.5, but we'll review it yet again. So here's what Newton's Law of Cooling says. The rate at which a body cools is proportional to the difference in the temperature between the body and the environment around it. A lot of times people will call the environment around it the ambient temperature. So the temperature F of T, and usually people would call that capital T equals F of T, of a body at time T, after being introduced into an environment, and the environment had a constant temperature of T0, that's the ambient temperature, is T is equal to T0 plus C e to the minus KT, where C and K are constants. And so, for example, it will talk about, as an example, a pot of coffee with temperature 100 is set in a room that is much colder. Well, the coffee will cool. Now, this also works for heating as well as cooling, and it's ascribed to Newton. So we're going to work two very quick examples of this, and they're both dealing with the same thing. Cooking meat, and CSI folks do variations of this to figure out times of crimes at scenes and so on and so forth. A roast is taken from a refrigerator at 34 degrees Fahrenheit. That means inside your refrigerator you have 34 degrees Fahrenheit, and you stick it into an oven that is preheated to 350. Now that means you're taking something cold and putting it in a hot environment, and you're maintaining this 350 degrees. That is also Fahrenheit. And after 1 hour, you've got a meat thermometer that you put in this roast, and the meat thermometer registered 70 degrees Fahrenheit. And so the first question is, what is the temperature 90 minutes after it was put into the oven? So that's the problem that we're going to be addressing. And so let's start working on the problem. Now, we knew that at t equals 0, we knew that the temperature of the meat, well, let's write the equation first, okay? So it's T equal T0, that's the ambient temperature, plus C, and this is e to the, I'm just going to call that KT. Minus KT is if it's cooling. If it's heating, we'll figure out what K has to be. So at t equals 0, what do we know? Well, this is the general equation. When t is equal to 0, e to the 0 is 1, so I know that the temperature is 34 is equal to the ambient temperature, which is 350, plus C times 1. That means the only thing that is unknown here is C, and we figure out that C for this problem is minus 316 degrees Fahrenheit. So that means our equation is this: T is equal to 350 minus 316 e to the KT. Now we have another data point because we know after 1 hour the meat is at 70 degrees Fahrenheit. So we're going to use this equation and the 70 degrees to figure out what K has to be. And so now it is T equal 1. So at T equal 1, we have 70 is equal to 350 minus 316 e to the KT. So we're going to subtract this from both sides, and we will get minus 280 is equal to minus 316 e to the KT. And we're going to divide both sides by that, and the minuses will cancel. So what we're going to have is that, I'm taking natural logarithms, so I have the natural logarithm of 280 over 316 is what we have on that side, and this is equal to, already divided by that, so this is the ln of e to the KT. And by the way, t is 1 hour, so that is ln of e to the k. So that's going to tell us that k is approximately equal to minus 0.12095. Now the students should check and make sure you know how to get these numbers, but now what we can do is, the question is really asking us, what is the temperature 90 minutes afterwards? So now we know what K is, so we know the real equation. It is T equals 350 minus 316. This is e to the minus 0.121. I'm going to put 1.5 in for T, and I'm going to get approximately equal to 86.5 degrees Fahrenheit. So you see, in an hour and a half, the meat has risen to an internal temperature of just short of 90 degrees. Now, the second question really deals with the same type problem. I'm going to use the information that we had, that we already have obtained from the first one, because now we want to say, suppose you want to serve this meat at 145 degrees Fahrenheit. That is not the way I like my meat. This is extremely rare, but they're going to do this anyway. So you know it's done by the meat thermometer. So what's the cook time? How long is it going to take it to reach that? Well, we know the equation was this. T is equal to 350 minus 316, and this is e to the minus 0.121 T, and we want this final temperature to be 145, so this is what we're going to solve. So we're going to subtract that from both sides, and we will then take logarithms. Let's subtract from both sides first. So it is 205 over 316 is equal to e to the minus 0.121 t. Now we're going to take logarithms of both sides. So we get the ln of this number over 316 is equal to minus 0.121 t. So we will divide both sides by that, and we will get t is approximately equal to 3.576 hours. So that's our example of Newton's law of cooling, or in this case, Newton's law of heating. And that really concludes our lecture for today. Thanks for watching. Do the math. It will make you strong.